SpaceX wants to land its rocket vertically on the moon. And on paper, it sounds pretty straightforward. The vehicle stands tall and stable on the launch pad. But once you take that same design to the lunar surface, things get a lot more complicated. In fact, a report from the NASA Office of Inspector General has raised some serious questions about whether this approach is as practical as it seems. So today, instead of just breaking down the challenges of how SpaceX plans to land on the moon, we're also going to take a look at a pretty unique solution that could help make it all work. The lunar version of Starship, often called Starship HLS, is massive, standing about 52 meters tall, roughly the height of a 14-story building. It's an impressive piece of engineering, but that size also brings some unique challenges. For the Artemis program, NASA is aiming for the moon's south polar region. Unlike the relatively flat landing sites from the Apollo program, this area is rough, uneven, and full of slopes that can reach up to 20 degrees. That's incredibly steep when you're trying to land a spacecraft that weighs tens of tons and towers over 50 meters tall. And this is where physics starts to work against you. Taller vehicles have a higher moment of inertia, which means once they begin to tip, it's much harder to stop that motion. NASA's current requirements only allow for about an 8-degree tilt at landing, so the margin for error is pretty tight. In other words, the ground has to be nearly perfect. Compare that to the Apollo lunar modules, which were much smaller and far more stable. The Apollo lunar module stood only about 7 meters tall, around 7 times shorter than Starship HLS, making it far less likely to tip over on uneven terrain. And we've already seen how unforgiving the moon can be. In February 2024, Intuitive Machines landed the Odysseus lunar lander, which was only about 4.3 meters tall. Even at that size, it still tipped over after landing. That really puts into perspective just how challenging it could be for something as tall as Starship. One of the more unusual challenges that comes with Starship's height is something you don't normally think about on a spacecraft: the elevator. On Starship HLS, the crew cabin sits near the very top of the vehicle. To get to the lunar surface, astronauts would have to ride an external elevator down from roughly 10 stories up, just to start their moonwalk. That same system would also be used to move equipment between the surface and the habitable section. And here's where it gets a bit concerning. According to the NASA Office of Inspector General, the elevator is currently the only way for astronauts to get back inside the spacecraft after working outside. If it jams or fails while the crew is on the surface, there's no backup route, no ladder, no secondary access, nothing to climb back into the pressurized cabin. SpaceX is actively working on adding redundancy to make the system more reliable, but NASA still considers it one of the biggest potential risks to astronaut safety. For comparison, Blue Origin is taking a very different approach with its Blue Moon lander. At about 16 meters tall, it's much shorter, so astronauts can simply climb down a ladder to reach the surface. No elevator required. NASA usually designs critical systems with what's called single failure tolerance. Basically, if one component fails, it shouldn't put the entire mission, or the crew, at risk. SpaceX is trying to meet that standard by building a more robust, redundant elevator system, while engineers from both NASA and SpaceX continue exploring backup options to make sure astronauts always have a safe way back inside. And Starship isn't just tall, it's huge. That size creates another major challenge. What happens when its engines fire close to the lunar surface? On Starship HLS, the rocket exhaust plumes interact directly with the moon's surface during landing. That might sound straightforward, but in reality, it's a pretty chaotic process. As the vehicle descends, those powerful plumes blast into the ground, kicking up massive amounts of lunar dust, soil, and even small rocks. This can interfere with precision landing and even mess with the spacecraft's navigation sensors right when accuracy matters most. We've actually seen a version of this problem before. During the Apollo program, astronauts reported that regolith, the moon's loose surface material, was thrown up by engine exhaust, sometimes obscuring their view during the final moments before touchdown. And those landers were far smaller and less powerful than what's being planned now. To deal with this, the Human Landing System program is actively working on ways to reduce the risks from plume-surface interactions. Right now, a lot of the modeling is still based on reconstructed Apollo data. The problem is, without real-world data from something as large as Starship HLS, there's still a lot of uncertainty. The risks can also change depending on the lander's design, how it operates, and even the exact landing site. Both SpaceX and Blue Origin are building single-stage landers, meaning the same vehicle handles both landing and liftoff. That's very different from Apollo's two-stage approach, which used the Apollo lunar module with a separate descent and ascent stage. And since these new landers are significantly larger than anything used during Apollo, they could create entirely new hazards that we haven't fully seen or fully understand yet. Now, there's an interesting idea that sometimes comes up when people talk about solving the landing challenges of the Starship human landing system. It's not exactly simple, but it's a concept that engineers and space enthusiasts have discussed quite a bit. What if the spacecraft didn't have to land vertically at all? In other words, instead of standing upright like a rocket, the lunar version of SpaceX Starship could potentially land lying on its side once it reaches the moon. The vehicle would stay in a horizontal position and touch down that way, with specially designed landing legs extending from the side of the spacecraft to support it on the surface. At first glance, it might sound strange, but the idea actually has a few potential advantages. For one thing, a horizontal spacecraft would naturally be much more stable. Its center of gravity would sit lower to the ground, and the landing legs could be spread over a much wider footprint. That could make a big difference when landing in rough areas like the moon's south pole, where slopes can reach 15 to 20 degrees in some regions. It could also make operations on the surface a lot easier. If the spacecraft were lying horizontally, the interior would already be much closer to the lunar surface. Astronauts could simply walk down ramps, and large cargo or equipment could be unloaded through cargo doors instead of being lowered from a tall hatch. There's also another reason this concept comes up: the possibility of turning Starship into a permanent lunar habitat. SpaceX has occasionally talked about the idea of converting landed starships into early moon bases. If the vehicle were already lying on its side, it could be easier to access and modify the large internal tanks and compartments that make up most of the spacecraft's volume. On top of that, future lunar bases will likely need protection from radiation and micrometeorites. One common idea is to cover habitats with several meters of lunar soil, known as regolith, which acts as natural shielding. If Starship were lying horizontally, it might be easier for robotic equipment to pile regolith on top of the vehicle, effectively turning it into a shielded base on the moon. Of course, landing a 50-meter spacecraft sideways would bring a whole new set of engineering challenges, mainly because of basic structural physics. Rockets like SpaceX Starship are essentially long, thin cylinders, and that shape is incredibly strong when it's standing upright. When the vehicle is vertical, most of the forces travel straight down along the length of the structure, which is exactly what the rocket is designed to handle. A simple way to picture this is with a soda can. If you place a can upright, it can actually support a surprising amount of weight, but if you put that same can on its side, it crushes much more easily. The same principle applies to rockets. Their cylindrical shape is optimized to carry loads vertically, not sideways. That's why Starship is designed to launch and land vertically, with its weight supported through the base of the vehicle. If it were to land horizontally, the forces on the structure would be completely different. Instead of the load going through the bottom of the rocket, the weight would press against the side of the propellant tanks, and the landing legs would have to hold the spacecraft in a way it was never originally designed for. To make horizontal landings possible, the vehicle would likely need major structural reinforcements to prevent bending or buckling. The problem is that those reinforcements would add a lot of extra mass. And in spacecraft design, extra mass is one of the worst things you can add, because it directly reduces performance and payload capacity. It's true that Starship already experiences some sideways forces during its famous belly flop descent through Earth's atmosphere. But that situation is very different. During that maneuver, aerodynamic forces are spread across the entire body of the spacecraft. A horizontal landing, on the other hand, would concentrate the loads on just a few landing legs, creating strong bending forces through the middle of the vehicle. Even though the moon's gravity is only about 1/6 of Earth's, the stresses during touchdown could still be significant. Some people also argue that a horizontal spacecraft would handle slopes better. But for missions in the Artemis program, landing sites will be carefully selected to be relatively flat and safe. And the argument about being closer to the ground isn't always decisive either. A A simple elevator can solve that problem, and being higher above the surface can sometimes be beneficial. For example, solar panels or antennas can work better when they are elevated. In reality, both approaches have their own strengths and weaknesses. A vertical lander keeps the structure simple and efficient, while a horizontal design could potentially make surface operations easier. And if there's one thing we've learned from Elon Musk and SpaceX, it's that designs can evolve quickly when new data appears. Right now, the company prefers a common Starship platform that can be used for many missions. But if operations on the moon reveal new challenges, the design could absolutely change. Some engineers have even suggested that building a specialized version of Starship, optimized for horizontal landing on the moon, wouldn't be that unrealistic. SpaceX already develops multiple variants of the spacecraft, and the company's philosophy is to build vehicles on a large scale rather than producing just a few units. With that approach, designing a new version specifically for lunar surface operations might eventually make sense. Vertical or horizontal? What do you think would work best for landing on the moon? Let me know in the comments. If you're interested in fascinating engineering challenges like this and the future of lunar spacecraft, make sure to subscribe for more, and I'll see you in the next video.